if you don't, yeah. Uh, and I will start sharing the screen. Do you see my screen, everybody?
Yep.
Yes.
Amazing. Okay, let me just reorganize a little bit. Okay, awesome. So let me do that. Okay, so first of all, thank you for joining us today, and thank you for newcomers and returning listeners. That's very valuable for us. And we usually try to hold these webinars about every 3 to 4 weeks, depends on our capacity. Different themes. And today we're talking about functional thinking. It is something that we're trying to somewhat kind of introduce into the world, this even term of functional thinking. There is always a functional modeling that's thrown around, especially people familiar with that from a trees world. But whoever is not, and we not necessarily trying to target people with an experience from trees, but more a wider audience, we try to introduce this thinking concept, and specifically in this case, it's a functional thinking. And what we're trying to achieve with the functional thinking is, how do we fund the wins and not losses? How do we actually invest in the right place and not waste our cycles and our wills? We usually start with a quote, in this case, a quote from Warren Buffett. Price is what you pay, value is what you get. And that's exactly what we're going to talk about today. So let's kick it off. First of all, we usually always start we try to dig into a definition. In this case, definition of what thinking is. There's multiple definitions. They're all around the internet, and you can find a lot of them. A few that we liked is John uh, Dewey, if that's the right pronunciation, I'm not sure. Thinking process is the process of solving doubt and uncertainty through reflective inquiry. So, there is already some sense of like solving some sort of problem in there, but in terms of thinking process, right? Jerome Brunner, thinking is going beyond the information given. So here we're getting a sense of being creative, having an information that we have at hand and creating something new out of it, right? Being creative, that's interesting. Lev in 1934, he said thinking is not merely an expression of ideas, but active creation of connections between them. Again, an interesting connection into something that we want to create for future, some creativity, right? Edward de Bono, a creator of lateral thinking, actually. Until we started working on it, I didn't even know about that. But thinking is a skill of considering things wherever they come from to make better use of them. In a sense, it's kind of the same thing, right? We have a bunch of ideas, we have a bunch of information, and we want to create something new out of them, right? Again, creativity, potentially problem solving. And then, of course, Cambridge Dictionary. That's the favorite one of all. We usually using Cambridge Dictionary for these things. Thinking is activity of using a mind to consider something carefully or to form connected ideas. Again, under the same realm, right? So whether you want it or not, thinking is about being creative, creating something new out of what we already know. Now, of course, we couldn't do without it, but we came up with our own definition. And thinking is a purposeful process of transforming insight about a problem into an actionable knowledge for generating future value. Right? So in the more simplified terms, thinking is a transformation of a problem insight, what we know about the problem, into the future value. Right? And value could be monetary value, it could be any type of value, but how do we transform the problem that we have at hand into the future value, in other words, innovation? Now, there is a lot of different types of thinking out there, and we have 7 of them here, but I'm sure there is more of them. These ones are fairly popular, right? Like critical thinking, creative thinking, design thinking is a lot of used in design tasks by product managers and people like that. So all of these types of thinking, they cognitive strategies. So it's a strategy of how these are methodologies that help us think again, help us to do the most difficult thing of all. But each and every one of them, first of all, it focuses on specific goals, not necessarily the same thing. It's not necessarily clear that we're going to get exactly the same result out of different thinking, different types of thinking, even though we might work on the same problem. But most important, they actually defining the what to accomplish and not the process of how to accomplish it. Right? Now, another point that I wanted to make here, the fact that we have so many definitions of what thinking, what type of different thinkings are, it means that there is no good definition of what it actually is. Right? It's kind of, if there is a lot of definition, there is a lot of different understandings, it means nobody has a really good understanding of what it is. And I'm sure there's a lot of studies about that, and I'm not the one to answer these things, but it is what thinking is, and AI just shows more of that. It's a complex topic. Now, given that we have all of these different thinkings and the lack of understanding of what of them, people typically falling back on the most popular one. And the most popular one is trial and error. We see it in the industry where the brainstorming happen, and let's try this, let's try that. We go and implement some sort of proof of concept or something like that. We fail, we're going back to the drawing board. So it's a test, fail, try again, test and fail, and try again, right? All of these methods, they are this method is again very popular. It's even utilized by animals, right? For example, there was a experiments with ants, right? That they were trying to get through some shape through a maze. They tried different ways. Eventually, they succeeded. But what does it mean? Try different ways, and eventually they succeeded. It means it's very wasteful and expensive, right? It is a method, but it's not. But without having a structured approach to how we're actually gonna solve this problem, and all we have is trial and error, is just very, very expensive, right? And this is why you hear a lot of times, let's make these trials very quick, so we're not wasting money, right? So instead of trying to use a different methodologies, companies and people try to make these trial and error cheaper. Now, what these unstructured thinkings leads to, it leads to complexity. And here's an example.
Alex,
Yep.
Dave
Sorry.
I
missed it.
Just a comment. I don't know if you guys have seen it yet, but on Prime, there's a documentary called The Thinking Game. Has any of you seen that?
No.
If you haven't, it's kind of cool. I actually saw it last night. It's an hour and a half long, and it's about AI, and it's about, trial and error on how some of the AI methodologies are working. It's very interesting. Just put a note down, The Thinking Game, Prime.
Okay.
Believe it's on Prime Video. If you got that, go check it out. I think you'd enjoy it because it's talking a lot about what you're talking about here.
Yeah.
Amazing. Yeah, we'll for sure do that.
Thank you. Let me add one more thing. I remember very good from very big company was task force to reduce cost of the product, and we were sitting in the conference room, and manager said, "No, have you prepared projects?" And I said, "Yes, we have 6 projects on cost reduction." He said, "No, you should prepare 60 projects, and maybe a few of them will succeed. So he's ready to fail. He's ready to waste money. And this is not good. This is a terrible strategy. As a result, our customer have to pay for our stupidness, our inability to solve problems and to make a good project.
Right. Another example that I actually forgot to mention as well, we did have a conversation once with a innovation lead, innovation manager, or VP of innovation, I believe, and his approach was that they working on as much projects as possible, and typically 1 out of 10 is actually bringing some value. It means that their project costs 10 times more than it actually is, right? Because again, the same animal understood strategy of trial and error instead of having the analysis in place and having being able to approach it in a structured way. Now back to this. What does it lead to, this unstructured development or unstructured thinking, right? One of the examples, we both coming from the microelectronics industry, that's example that's very close to us. And over the years, the number of interconnection layers in microchip manufacturing increased exponentially. I'm not sure which year this image is from, but I think right now it's over 20 layers of interconnection. What does it mean? It means complexity. It means cost, right? And over the years, the cost of a single wafer increased exponentially, as we can see on this graph. But it's not only the cost of it's not only because of the value of the product that we're releasing, right? But it's a cost of complexity and complexity of manufacturing of that. And this is another example in here where the project on 28 nanometers was the process of 28 nanometers was around the 400 steps, right? I'm not sure, I don't remember in terms of time how long it took, but the 5 nanometers, it's over 1200 steps, right? And the big majority of them is actually cleaning steps. What does it mean? It means that we're adding additional complexity to the process because we don't know how to solve the problems, right? And cleaning steps, as an example here, it means it's as we've seen in other webinars, the cleaning steps, it's a corrective function, and corrective function by definition is to remove the deficiency of some previous functions, right? And it means that if we increasing these cleaning steps as just one of the examples, it means that we don't know how to do it efficiently enough. So the only thing that we can try, going back to trial and error, is to wash it again and clean it again and do it again and again. What does it mean again? It means additional equipment, additional cost, additional time, and so on, right? And who is paying for it? The customer. Now, going back to functional model and functional thinking, as we're trying to introduce it here, every time we're building something, we typically will build a schema, right? Or some sort of diagram. In this case, it's a electronic schema. It could be UML diagram from a software engineering world. It could be many different types of diagrams or schemas that we can draw to help us build the thing, help us build the device. These charts, these diagrams, they usually talk about the components and the connection between the components, but they don't talk about function, why these components even there. Also, many times you will, for example, take this kind of schema, you will construct a schema on a board, and it's not going to work. Without understanding the function of each and every one of these components, there is no way you will understand why it doesn't work. And the only thing you can do is recheck yourself, potentially, take it all apart, put it back together, and hope for the best. Again, back to the same trial and error of problem solving. Functional thinking actually takes a little bit different approach. First of all, every system will have a product, right? Every system that we build for a particular reason, either to create a product, increase a value, change a parameter in some sort of way. So we're defining a product. Now, in order to produce this function that we're looking forward to it, we have a component of multiple components and doing that. And to support this function, the system sometimes getting much more complex, and these complexities coming as a collection of components with functions between them. And of course, there is a super system, which we'll talk in a second. It's the external components which potentially affect us or we affect them, but we cannot change them or we're not even willing to change them, right? But it's when we start to understand the functions between the components, we start to understand how the whole system functions and where the inefficiencies are and where the wastefulness is, and potentially where the problems are as well, right? So how do we typically build it? It's kind of a step-by-step. So identify the product. That's probably the most important thing out of the whole functional modeling or functional thinking. Identify the product, why the system is in there, right? We many times take a car as an example, and we created the car to move people, move things, right? So in case of a car, the product could be people or cargo or whatever it is that we're trying to move, right? Now we need to identify the components as the next step. The components are all the components that enabling the system to produce the function that we need to produce. Okay, identify supersystems or supersystem components as we call it here. Supersystems, they are components that part of the system or playing some role in the system, but we can't really affect them, like an atmosphere around us, the road that we're driving on. It's not something that we can really change as part of working on a car. Maybe sometimes we can. And then identify the functions. That's the last extremely important piece, understanding the functions and mapping these functions between the components and the product, and so on. So understand how the entire system works. Then once we have mapped this model, and we have the entire picture in front of our eyes, we can analyze, we can start thinking again in terms of functions and make appropriate decisions. Now, typically, this is just an example of how a functional model might look like, right? Again, there is a product, there is multiple components, there's super systems, there's different functions and different types of functions. There's a harmful, useful, excessive and insufficient. We might go into that a little bit later, but most important things, while you're building this model, it forces us to understand how our own system works, right? So we've seen many cases where people, working on their own systems, and yeah, we know how the system works. Of course, we know it's our system. But when they start building it, they realize that they know nothing. Well, not nothing, but they don't know details enough to actually make the decision. And then without having this visibility, again, coming from a software engineer world, it's very, very typical where you have people trying to make a change, but they're scared to make a change because they don't really know what's there. And now they start adding additional layers and layers and layers. And what these layers are, again, additional complexity because of lack of understanding of how the system works. Now, once we build the model, we can, and that, by the way, that's a screenshot from the PRIZ platform. The platform does a whole bunch of different calculations. In particular, we calculate the functional rank and problematic rank of every component. Functional rank is basically an indicator of functionality or value of the component. And of course, problematic rank is the one that indicates that that this component contributes to the problem in the system or problem that eventually reflects on the final product. Using these parameters, we also can calculate things like operational effectiveness, basically how effective our system is given this model. Let's take it even further. If we see components that have a functionality like component 4 in here, basically it means that this component brings the most value for the product. If we want to invest in that, if we want to invest anywhere in the system, we should invest here. We should develop this component for. Now, there are some other components like have some functionality, but they also have problematic rank. In this case, very high problematic rank. These are components that typically create the actual problems in a system. And problems could be, they do have a functionality, they've been put in place for some reason, but they're actually creating more problems than bringing value. These ones we need to either remove their problematic functionality from there, or even get rid of the component altogether. And we have the components that either have a very, very low functionality or no functionality at all, basically no impact on the final product. These are the ones that we need to ask ourselves, why are these components even there? Because if we're able to remove them, it's a cost saving, it's simplification of a system, it's cost reduction for the client, and so on. It's less problems down the road as well. So if we're talking about process improvement, cost reduction, this is where we should focus. Anatoly?
Dave,
Yeah, I have a question, like component 6 there in the upper left. Component 7 does something useful to component 6. And you say component 6 has no impact, but I'm sure if you were to ask somebody, hey, let's get rid of component 6, they'll very quickly jump back and say, well, we can't get rid of 6 because it does this. So my question is this model just not complete? Because I can't imagine very many systems where you have a component that everybody says, I don't know why the hell we put that in there. It doesn't do anything.
That's exactly the point.
You know what I'm saying?
Exactly the
yeah.
But that's exactly the point. When we start working on modeling this, for example, one person, I can start model a system, and I know what I know, right?
Yeah.
And I can, from my perspective, I can say, wait a second, component 6 is not needed. But when we have that conversation across multiple people, somebody might know something that I don't. Right? This is where the entire collaboration, and this is why it's very, very important to have multiple people working on this thing, not necessarily even engineers only, because
but so then they answer that why 6 exists, and then you create another bubble there on why it exists, and it goes from no impact to some impact.
Potentially, 100%.
Okay.
100%. Benjamin?
I just had one example of component 6 just happened to me. And in the insurance business, new submissions for new business arrive at this insurance company, and then they have to be documented in a system, right? And then the underwriter determines whether or not they want to write the business. And that it was completely useless function, because the underwriter should first determine where they want the business before it ends up getting logged in this particular system. So in that case, this component was serving no value. And I wish I had done a functional model with them before they started creating architectural diagrams.
Here's a good example. And that reminds me another example of we working with one of our clients in Europe, and they have a manufacturing process. In their process, the QA people, they always getting involved, right? But probably in about 70% of these steps in their process, the QA themselves, all they do, they just get the information. They consume the information, but they don't produce anything back into the system. So they kind of observers. They can't control, they don't do anything in these particular steps. They kind of consume the information. So from a product perspective, they have zero value.
And then
they might control it later, but in one or a few particular steps, nada.
And I see component, and maybe this is, tell me if this question's inappropriate, but I see component 4 has a value of 6. That blue bar going across has a 6 on it. I imagine that's big value. And I'm not sure where the 6 came from, but is that because it's closer to the end product? And it only has, looks like one output, which is a useful function. And maybe,
Right. So
Yeah,
again, in this
it's
particular situation, it's more of an example.
yeah,
Again, it's not
okay.
a real system. We will touch a real system. But yes, the calculation depends on the type of a function and the distance from the product as well.
Okay, that makes sense. Yep. Do you ever bring cost into it?
no,
We
Okay.
thought of it,
not
but
yet.
it's not as trivial as it sounds.
Yeah, value is a ratio of good stuff to bad stuff, and bad stuff is problems, and bad stuff is cost.
Yeah.
Right.
Yeah.
But again, it's not as, because think about it, the entire modeling concept is very subjective, right?
Yes,
So
agreed. Yep.
one can say that the problem is overheating, right? Another one say it's a cost. Somebody else can say, oh, I just don't like that component, right?
And
It's too much maintenance. You name it. So
and
yeah,
there's
go
so
ahead.
many lenses that you can look through value with,
Mhm.
and you kind of have to choose, one at a time anyway. If you're going to
Yeah.
try to quantify value, that would be really
Right.
complex. But
Yep.
keep
Right.
working on it. I want to see.
That's kind of what this is trying to do, is calculate value. You see them rank ordered from the top value to the
Yeah.
worst value on the bottom, and then you can decide how to optimize your system based on that priority. Yeah.
Exactly.
Right. But again, it's the quantification is the difficult part here, because what does it mean? Right?
So this is a
It's a
relative value of function.
Yeah.
This. Okay. Yeah.
Mhm.
Sorry to interrupt.
No, it's all good. It's
Excellent.
perfect. We don't have a lot of people, so we can have the conversation. That's perfect. So here's an example that we actually used it many, many times in the past as part of our training material, as well as one of the webinars. A vacuum cleaner, right? A vacuum cleaner is something that everybody knows what it is and what are we using it for. Seems to be a very simple thing, but again, once we start building this functional model, we think how complex this is. But it's not only about complexity, right? Because realistically speaking, if we think, why do we need a vacuum cleaner? We need it only for one purpose, to remove dust, right? We only need this particular basic function to remove dust. But in order to enable for the air to suck out the dust from the carpet, from the floor, you name it, from where, we built this extremely complex system to enable for the air to do that, right? We need the motor, we need the fan, we need a whole bunch of different components to actually enable that. So we're building complexity. And the most important thing, that we actually forcing our clients to pay for that complexity. They don't need a motor, but they forced to buy it because we didn't find any other way to do that. They don't need wires, but they forced to buy it because there is no other way to do that, right? All they want to remove dust. How we do that, how we enable them to do that, maybe I don't know, a click of a button somewhere and it's all done for them, and they just paying for the click of a button. That would be ideal for them, right? Talking about ideal system. But because we're so quote unquote dumb, and we're not able to solve these problems and achieve this basic function in a simple way, we're forcing our clients to pay for that. And of course, all the other things coming with it, as more problems, more complexity, more cost on our side, and so on. Longer production line, you name it. Now, also in here, we're calculating exactly the same kind of ranks and operational effectiveness of the entire system. In this case, the vacuum cleaner and operational perfectness. That's the ratio between the basic function that we need to relatively to the rest of the complexity of the system. And for example, we can see that the filter is actually the most problematic thing, right? Because really, if you think about it, we want to be able to create the suction as much as possible, but at the same time, we have a filter that stops the flow, right? Then the question is, why is it there? Do we actually need it? Can we replace it with something else more efficient, right? And achieve the function of stopping the dust or capturing the dust in some other ways, right? Yeah, there is cyclone type of vacuum cleaners, but it's still, there's something that stops that flow, right? They're a little bit more efficient, potentially. I don't know, I didn't analyze that. But still, there's filters, there's a bucket, there's, you name it, there's a lot of different components that we, again, forcing our clients to pay for. Now, let's assume another thing. Let's assume we decided to improve our vacuum cleaner and we decided to make it rechargeable. Great, right? It sounds even sexy. Rechargeable, I don't need to carry the wire around. But think about it. We have the same basic function, the same function that the client need. Not us, the client needs. And now, instead of selling them already complex system, we now forced to sell them a battery, AC-DC converter, and so on and so forth. So we, for the same basic function, we created even more complex system.
Yeah.
So again and again, the client pays for the complexity, and because we are not able to provide the function in a simple way, in a less complex way, this is what they're paying for, not for the actual value that they're getting out of it, right? And of course, when we're comparing these two models, you immediately can see them in these types of numbers that the effectiveness actually dropped. Right away, you can see that without implementing that, without building a proof of concept, without anything, because we can imagine and model how the future system potentially can look like, we can kind of predict the future, how is it actually going to look like from an effectiveness perspective. I'll pause here for a second if anybody has questions. All right, let's move on. So, a few success stories from the past, from real projects that we work on. We and Anatoly mainly worked on. This is, again, a project that we did demo a few times in the past, and we used it in case studies, and we used it in webinars as well. Microchip manufacturing for yield improvement. And the problem was that the wafer, during the cleaning process, there was still a lot of defects left, basically particles left that were creating defects on the wafer. The traditional approach that people took initially is introduce additional cleaning, right? What does it mean, additional cleaning? Additional equipment, additional time, additional steps, all of these fun stuff. So the project was successful in terms of introducing the additional cleaning, right? Because it's a lot of work, especially in microchip manufacturing. It's actually a lot of work to introduce this kind of process. The project itself was successful.
Good quick question. Is the defects the amount of dirt on it, or is it something else?
In this particular case, it's the amount of particles that are not supposed to be there.
Okay, all right.
Right, and you can call it dirt. Yes, of course.
Yeah, that's what I meant.
Yeah, yeah.
I'm still thinking vacuum cleaner. Sorry.
Okay, I see.
You know what? It could be a solution here because all you need to do is actually remove the particles, right? Maybe instead of washing, you need to vacuum it. I don't know. Speaking of a function, right? Now, the result, of course, again, as a result of that successful project, yes, it was decided not to do the additional cleaning. Everything is fine. It was executed perfectly, but it introduced higher cost. And the most important, there is no learning. There is nothing that people learned out of it, right? There is no understanding why did it happen. But if we do the functional thinking or functional analysis in different term, all that the decision was just to increase the pressure in the chamber, right? There is no impact on the cost because there was no, basically it's a little bit of a tweak of the same step in the existing process. Increase the pressure within the same chamber, right?
Yeah.
Again, from my perspective, the most valuable piece out of it, it's actually understanding, it's actually the learnings that we can take further, right?
So
And based our
that additional cleaning was a corrective function, would you say?
Mhm. Well,
Yeah.
this whole thing is corrective function,
Yeah. Okay.
right? This whole thing is corrective. Ideally, if we didn't need the cleaning in the first place, that's the ideal system. But again, microchip manufacturing, huge corporation, very hard to do things like that. But it's a little bit easier to introduce tweaks and changes and parameter changes, right? And again, the most important thing is learning that we can take further as part of the continuous learning cycle for everybody inside the corporation, right? Another example, also from microchip manufacturing, wafer breakage. Again, we used this example many, many times before, also for root cause analysis as well as functional modeling. What was happening here is inside the chamber, the wafer was breaking, it was shattering, or some percentage of that was shattering, right? The traditional solution that people actually came up with was to identify the equipment that was breaking these wafers the most and take them out. Basically shut them down. But what does it mean? Longer process, more expensive. Again, no understanding why did it happen in the first place. So there's no learning, there's no guidance for future development, nothing, right? It's kind of a patching of a problem. If we analyze that properly, there is the solution was to redesign the pedestal a little bit. So yeah, apparently the wafer was flying on during the flash heating because of the gradient of pressures. Fine, let it fly, right? As long as we design the pedestal in a way that even if it flies a little bit, it doesn't actually break it, and that's fine, right? So again, the problem was solved. The only cost was the one-time cost of implementing this new shape of a pedestal and the learning out of it, right? What can we learn from it further? Next example, again, microchip manufacturing. That the problem was that it was identified that if we wait too long, the tests on the microchip was failing, right? Well, that's a traditional solution again, because there's no there was no additional analysis into that. The traditional solution was, oh, let's add alerting system that will say this wafer is sitting on a side for too long, right? So alerting system is great, but again, lack of understanding what the reason is, and no guidance for further development. And again, it's additional system, additional complexity, additional constraint, additional cost. The actual solution after analysis, it was that after understanding the chemistry behind the reason, all that needed to be done before, it doesn't matter how long the wafer was sitting around, they needed to wash the wafer just before the measurement, right? Yes, there is a little bit of a cost, additional cost into that, but if before the wafer is being thrown away completely, now they are not thrown away, right? So this small, cheap, relatively cheap additional wash of a wafer basically solved that problem altogether. Understanding the mechanism of the failure, right, through a functional analysis. Another fun example is, again, it's a real example from a real industry. People were falling on the stairs, on the stairway. The traditional solution, again, it was put posters everywhere. Keep the handrails, use the elevators, don't come here, don't go there, a bunch of different restrictions. No understanding what happens, no additional development going forward. But the actual solution was to distract people's mind from walking on the stairs. And once you distract it, you're forced to hold a handrail. Right? So, you walking somewhere in a fairly dangerous situation, and these are real pictures that were put on the wall. They were funny. People were distracted in these pictures. When they distracted, they automatically were holding on the handrails. Funny, interesting solution, has nothing to do with technology as well. That's another thing to understand here. It's not only the engineering systems that we can apply it for, it's any system of people that we can apply it for. Another thing, I'll just go quickly on that. People were the rotation turnover of engineers in the plant was fairly quick, 2 to 3 years. It's, we all know it's additional cost of training, onboarding, hiring. It's an extreme cost, especially in manufacturing plants. It could be, at least a year until a person becomes actually productive and brings real value into the plant. They did at some point implement on-job training to ensure faster integration. So instead of solving the problem of turnover, they try to make the people more efficient when they onboarding. Great, but doesn't really help. They still leave. So after analyzing why they leave, this was, I believe, a combination of functional model and perception mapping as well. They needed a career path, clear career path. Yeah, Dave.
Oh, no. No
Oh,
question.
no, I thought
I
you
was
raised
just
it.
rubbing my hand the hood. Sorry.
No worries. No worries. Right, so result, they implemented the process, how you create this clear career path, also recognition process, and so on and so forth. So people actually felt valuable inside the organization. Now,
I'm so sorry. HR guys suddenly reveals that they have to work. They have to do something.
yeah.
Mhm.
Yeah, which that's another interesting aspect that many times these analysis, they actually help people solve the problem, but it's not necessarily true that every person actually wants to solve the problem, if you will, right? Because
Mhm.
the fact that everybody wants, the process of solving the problem because this is what they're getting paid for, but they don't want it to be actually solved because all of a sudden they getting out of their comfort zone. Somebody can be on the same position solving exactly the same problem for 2 years. He's comfortable there. He's reporting once a week. He's getting his salary. Everything is fine. And all of a sudden, some sort of tool comes in and first of all, he needs to work hard because it is a hard work to do these analysis. It's not a simple click of a button. But also, once he solves the problem, all of a sudden he's kind of out of employment, or that's what he thinks that he's out of employment. I would say that's completely wrong, but many people think exactly this way. Now, so let's do a little bit of conclusions here. So functional modeling really drives simplification, right? Again, going back to thinking about components, and if we only think about the components, we can only focus on the component itself, and we start trying to improve the component and invest in that component, and we don't see anything else but that component without necessarily even understanding what that component is built for, what's its function. So at the end of the day, the component might be as perfect as you possibly can imagine, but the entire system of which that component is part of becoming more and more complex, right? If we switch our mindset into functional thinking and we think about the function that we actually need to achieve, components aside, remember that example about the basic function, removing the dust, right? If all we think about is how to remove the dust, there's all of a sudden a lot of different ideas how we can remove that same dust without motor, without the airflow, maybe it's a duct tape, right? And that would be enough. The same example that we
Dave,
Yeah, even better than removing the dust. How do you make it so there's no dust in the first place?
Yeah.
for
exactly,
example, perfect,
exactly.
right? So the fact that we are switching our mindset into thinking about a function instead of being bound to the existing components and trying to solve the problems with existing components, the knowledge about the function, the knowledge about what we can achieve, all of a sudden opens up so many opportunities into achieving that same function, right? Same example with a car. The car can move, being built to move cargo, people, whatever. But if you're just thinking about the function of moving something, you can move it in so many different ways, and you don't necessarily need a car. So you can find potentially much cheaper ways to do that, right? Now, of course, all of that leads to innovation. And innovation, in our mindset, the way that we're trying to promote it all the time, and we truly believe it's true, it's the simplification. It's all about simplification. If you add complexity on top of a system, it's not innovation. It's just just a complexity. When you create something truly more simplified, but achieving the same thing, that is something that we can truly call innovation. And I'll pause here before I switch to a platform. We kind of running out of time a little bit, and I hope people are okay with that. All right. So there's one example that I wanted to show. Let me share a different screen. First of all, for whoever is new in here, this is how our platform looks like. There is a, yep.
Alex, something happened with your voice. It's acoustic effect.
Sorry.
We
Is
hear
it
it
better now?
doubles. Now it's okay, yeah.
Okay, great. Sorry about that. So the platform is organized in form of projects, and projects, they basically, it could be something very small, a 5 minutes investigation. It could be 5 months work on whatever innovation that we're trying to work on. It doesn't matter. We still wrap it inside of a project, so we keep the entire context inside. In here, we have, of course, the overview, and the overview is everything that we originally know about the project or the problem space, right? Typically, that comes in emails or some sort of document or somewhere, sometimes from a manager or from other engineers. There is a problem statement, which in here, we didn't define it, but that's kind of the typical progression of how we going into solving a problem, right? We have the general information, then we're defining a problem that we're trying to solve. And then the core of the system, it's basically the set of tools that we have inside the platform. Currently, we have 12 of them. And the two that we typically using for functional analysis or functional thinking are functional modeling and process functional modeling. Functional modeling is what we've just seen in our presentation. The process functional model is one level up. So if functional model can potentially analyze one step in the process, the process functional model analyzes the entire process and then steps within it. Now, just one note about these things. We have pretty extensive documentation about each and every one of them, how to use them. And these links, they lead into these documents and guides. Now, one example that I wanted to show is this, that we prepared ahead of time a little bit because, again, as I mentioned, it's actually quite a lot of work to do these analysis. And it's the people structure or organization structure inside a typical manufacturing plant. Of course, it's not an exact science. It's based on our understanding. We're probably missing a lot of things, but just to, highlight the important piece, looking at this kind of org chart, it looks like the plant manager is the most important person in the organization, right? kind of that's org chart. That's the only conclusion that someone can come up with, and there is no additional tools that can show you otherwise. But if we try to model it and actually define the product of the manufacturing plant of the one that we're trying to do, all the people, and then some additional components like production equipment, a database, and so on. And we map it in a very simplistic way without going to the details of problematic or different functions. We just assume that everybody performs the work perfectly in the way that they designed to do. When we look at this, again, in a very simplistic way, without going into the details, when we look at these ranks that we calculated as a result of that, we can see that the most important person, or the most valuable component or people, is actually process engineers. Not the plant manager, not QA people, not anybody else, process engineers. So it means if you want to improve your operations, this is where you should invest the most. Invest means in this particular case, it could be additional training. It could be basically anything that will help them to do their job better, whatever that means, right? And then, of course, you have less. I really want to be careful about less valuable, but I would say less impacting, right? Again, given the model of how we build it based on our understanding of the manufacturing world. Did we make mistakes here? 100%. But it's just to show the example of the typical diagram shows one picture and very little understanding, and another diagram, which actually talks about the functions of each and every one of the components inside the bigger system, in this case, system of people, shows a completely different picture and shows and emphasizes a completely different understanding of this manufacturing unit, manufacturing facility, right? And of course, the more you dig into that, you understand more, right? Another piece, danger that people might see in that, they can say, wait a second, this is actually my job. Am I not needed anymore? That doesn't mean it, right? It means they might need to do something else, or maybe something additional, or change their focus into something else, right? It doesn't mean that reducing it.
Try to click the recommendations.
Yeah.
You see.
So recommendations, there's a few different types of recommendations that the system suggests, including for the inventive principles, which helps us to resolve contradiction between the different components. And this thing is developing as we go. And I will pause here.
Alex,
we at time.
Just one point. If you go to, can you go to model? Just shows that we can modify and make different versions, and actually we can.
Yeah. I will actually show it on a different one where we have already different versions. And that's actually this beautiful vacuum cleaner where we already have we already have different versions of the same model. Yeah. And this is the basic version that we just looked at. And that's the wireless version that we just looked at. And this is, we called it innovative version. You know, we kind of played with it a little bit, but what we can show here, we can show the comparison between different models, right? So the change from this to this, it's actually lower operational value, and we can see all of them, right? The innovative version, as simple as it looks, it's still not very efficient. But then we have a different proposal. We're thinking how we can improve it, and it actually did improve quite a lot. And this is with a piezoelectric belt, right? Is it achievable or not? That's a different problem to solve, right? In terms of implementation, but in terms of thinking of direction of how do we achieve the function of removing the dust again. Maybe we can do it with tweezers. Still doesn't, makes the work done. So yeah, we do have this ability to compare between the different models in the same project and the same tool.
Alex, what I really like about the functional model is it's very, very visual. And this may be a problem more in the US. I've worked with leadership teams in Japan and Europe, and in the US, senior leaders, like, they need permission to be uncertain. They think they always have to have the answer. And by making it visual, it makes it safe for the team to challenge their understanding of the model.
Right.
Or actually, if they begin to build the model, they themselves, the leader, will understand that they may not be seeing it clearly. So I think this is a really powerful way to level the playing field so teams and leaders can work more closely together. That's what jumps out at me. And I do love that you can have multiple versions of this, because we know that there is no perfect model, right? No perfect representation, right? But is it useful, right? So anyway, I think this is fantastic.
And you're absolutely correct about managers who don't necessarily, or they think they understand, but don't really understand. And the biggest problem with that is many times we speaking at different levels, we speak in different language, right? The language that engineers speak with, managers don't understand. So all of a sudden you have this translation layer between the engineers and the management, and now you have the engineer leads who do that translation. But what does it mean, translation? It's kind of description of the same thing in a simple words, but that means you're kind of helping them to stay, excuse me for my French, dumb, right? Instead of actually bringing them into the analysis session, for example, and make them being part of that
Right.
process. And this is when they, first of all, they contribute in exactly the same way as anybody else. They feel part of that solution as well. So it's very psychological. And they understand what the hell the engineer is actually talking about.
Right.
Right.
Yeah, that
So
shared understanding is so valuable. So valuable.
Absolutely. And that's why in every time that we trying to onboard a client, we always saying the manager should be part of the same training. They must understand how this process works. They must understand so that, sometimes you can't demand a solution tomorrow just because you want to. You can demand for a particular, once you understand the solution, you can demand for an implementation at a particular time.
Well, yeah. Well, once you understand the space, a leader then knows what to ask for, right? I mean,
That too.
Exactly. Exactly.
That too. Any other questions? I will stop my sharing.
I have a question.
Of course.
Your function modeling. I think that you said that you had a system function model or a product, and then you also have process. Do you have an example of a process map you could just pull up and just show?
Of course.
I'm curious how that differs as far as the elements and the nodes. Because the elements that you had on the first one was parts.
Right.
And then you had the functions between the elements.
Yeah.
I'm wondering if
so
this
is again, it's a project from the past. Obviously we didn't have the tools to actually do the project on the platform back then, but we kind of replicated it here to show as a case study. And the process here, Again, it's a furnace with multiple different steps for oxide deposition. And the problem was that there was a high sigma on the lower wafers, a high sigma of deposited silicon oxide. That's the problem, but it was a whole process how we loading, unloading, heating, preheating, the position itself, and so on and so forth. So when we looking at the process functional model, again, that's a description of the actual process in words. We always encouraging people to do that. It looks something like this.
Oh,
right?
it's very different. Okay.
It is very
It's
different.
that's sequential. Sequential.
Yeah.
Every process is sequential.
So it is sequential. Yeah. Okay.
Yeah. It is sequential. So in this particular case, we have the preloading, loading, stabilization of temperature, oxidation itself, unloading, cooling, and then the actual measurement. And
So
if you guys
you could click into any of those steps and see
you can click into each and every one of these steps, and you get into the functional model of that
Okay, so
particular
this
step.
is a step. So there's still parts of the process. The parts are the nodes, and the function are still the, the links. It informs, heats, moves, stops.
Yeah. It's still a functional model within the step. So every step is analyzed as a system, right? As a functional system.
Yeah.
And then when we put all of these together, we're getting a little bit additional analysis, right? First of all, operation types breakdown. And operation types breakdown, it's an interesting thing in any microelectronics manufacturing. The productive functions is somewhere between typically between 15 to 25%. The productive operations are the only ones that actually create value for the product. Everything else is waste of money, right? So if you want to reduce costs, innovate, simplify, make things faster, this is where you look for, right? Now, another thing.
I'm just curious. So the productive, providing, corrective, and metrology. Where did that come from? That looks familiar.
That's
I studied trees. I'm level 3 trees.
Okay, come from trees. Yeah.
Yes, and I not only studied trees, I used it maybe 30 years, 25 years at least.
Yeah.
And all this platform is not only, we just pick up some idea and convert it into software.
Yeah.
Here is a huge experience.
Yeah.
Very
I used to work.
time.
You've probably heard of Invention Machine before,
Sure,
right?
sure. I used.
I worked for them for about 4 years from Valery Surkov, and those looked kind of familiar.
right. So it is based off of that, yes.
Yeah.
Now, in this particular scenario, if you see something that I wanted to show, besides the analysis and what can be improved and where the wastefulness coming from and so on, the most problematic step is this, right? So if we want to solve anything in that problem that we described in here, we should focus in this step.
Yeah.
And going into functional modeling, I don't remember where exactly we showing that where the problem is, but basically the thermocouples were measuring the temperature all the time during the loading. So imagine yourself, you have the furnace is open and you start feeding this column of cold wafers into the furnace. These thermocouples reading, oh, I'm cold, let's add power. And then you're moving it more cold wafers. Oh, I'm still cold, let's add power. So over time, while you're loading it, the bottom part was always overheated because of that. right? So the solution was, again, simple. Disconnect the thermocouples during the loading process. And then reconnect them again to have during the stabilization period. Right? As long as we understand how the system works, as long as we understand how the process functions and why things there, then we can make formal decisions and actually solve problems properly.
Okay, may I add something? I want to say what's good in this approach when we created this process flow, when we created all functional models within operations. We found that the most problematic operation is loading. What does it mean? It means stop thinking about old systems. Stop thinking about flange. Guys spent 2 years to trying to redesign flange. They said flange is a problem. Stop thinking about this. Try to create model how you can increase sigma in bottom wafers during the loading. And when you formulate it, you find this model very, very easy and very fast. And, you know, it's like funnel. It says, think about this. And also, of course, if you go to summary, we also recommend to summary. We also recommend differently, to think differently, consider differently to different operations. If it's productive, consider improving, apply technology, invest money, training, everything, new processes, and so on. If you have providing or corrective operations, please don't develop it. Think how to eliminate it. From this point of view, when I see how people spend through money on photolithography, this is stupid. It's good for SML, but not for chips, because you know the product doesn't need photolithography. We should not develop, not invest money into this. We should invest money into eliminating this. And of course, metrology, we get a lot of numbers. We should think, do we do something with it? If not, eliminate it. Eliminate it.
Yep.
So, thank you.
All right. So we over time.
Yeah.
I will, if there's no other question, I will stop the recording.